Complex 1, or NADH dehydrogenase, forms the first oxidative phosphorylation protein complex of the electron transport chain in the mitochondria. Complex 1 translocates 4 protons for every 2 electrons that pass through it, although there has been some debate about the stoichiometric ratio. The exact mechanism by which proton translocation occurs due to NADH oxidation and ubiquinone reduction is currently unknown. The protein itself consists of a hydrophilic domain and a hydrophobic domain with separate evolutionary origins. Conserved electrostatic interactions exist between the two domains through hydrogen bonds and salt bridges among subunits NQO8 of the membrane arm and NQO4 and NQO6 of the peripheral arm. Thus, the coupling of quinone reduction to proton pumping most likely evolved one time and acts through subunit NQO8. Ubiquinone reduction results in the conversion of 2 ketone groups of the head group of ubiquinone to 2 hydroxyl groups. However, the order of the electron and proton transfer to ubiquinone is not necessarily known. Because ubiquinone reduction occurs in 4 steps, there are many pathways by which the reduction can occur. Brandt proposes a 2-stroke mechanism in which complex 1 switches between an electron transfer state, or E state, and a proton transfer state, or P state, 2 times to translocate 4 protons. In this mechanism, the protonation of ubiquinone in the P state following each electron addition in the E state provides the driving force to pump 2 protons. Although complex 1 contains 3 antiporter-like subunits, this mechanism relies on just a proximal module and a distal module to pump 2 protons 2 separate times. At first, complex 1 exists in an E state in which the half channels of both the proximal and distal modules remain closed. Upon the first electron transfer, 2 protons enter the half channels of both modules from the mitochondrial matrix. Subsequent protonation of the anionic semiquinone species occurs in the P state, which causes long-range conformational changes to pump out the 2 protons. The second electron transfer in the E state causes 2 more protons to enter both modules from the matrix. Then, stabilization of the ubiquinol anion occurs in the P state through protonation and results in proton pumping. Compelling evidence for this mechanism comes from EPR studies which indicate the presence of a fast-relaxing and a slow-relaxing semiquinone intermediate in complex 1. Increasing structural evidence points to a single-stroke mechanism in which the reduction of ubiquinone to ubiquinol causes 4 protons to be pumped out of the matrix all at once. In the single-stroke mechanism, 2 electrons are added to ubiquinone, which causes proton pumping, and then protonation occurs. This mechanism is predicated on a series of electrostatic interactions that generate conformational changes across 4 different proton translocation pathways. A recent crystal structure of complex 1 from T. thermophilus, resolved at 3.3 angstroms, has revealed the following properties: an enclosed Q chamber where quinone resides, a funnel of charged residues connecting the chamber to a distinct 4th proton translocation pathway, and a continuous string of polar and charged residues spanning the membrane arm of complex 1. Subunits NQO8 and NQO7 harbor the entrance of the Q chamber and form a narrow entry point that effectively seals the quinone head group from the solvent. At the bottom of the chamber, essential residues Y87 and H38 of subunit NQO4 have been found to hydrogen bond to the 2 ketone groups of quinone. These residues can protonate quinone after it receives 2 electrons. The enclosed Q chamber is necessary to conserve the negative charges generated from the reduction of quinone. Charged residues extending from the Q site to a glutamate aspartate quartet in subunit NQO8 interact electrostatically to generate the first conformational changes in the protein. Proton flow in the 4th proton translocation pathway is conceivably regulated at this quartet. Superimposition of the core fold of NQO8 with the half-channel folds of the other three antiporter-like subunits shows a low root mean square value and conserved polar residues. This provides further evidence for the fourth proton translocation pathway, with one half-channel in subunit NQ08 and the other half-channel by subunits NQ010 and NQ011. The other three proton translocation pathways are connected through the continuation of the hydrophilic funnel down a central axis to the membrane arm. Polar and charged residues along with surrounding water molecules interact with each other at the connections between the half-channels to contribute to the conformational cycle. Specifically, these residues could mediate changes in pKa, which would result in proton pumping. Furthermore, the transverse helix HL and the beta H element assist conformational changes by holding the discontinuous transmembrane helices together. Both the single-stroke and the two-stroke mechanisms rely on electrostatic interactions to generate long-range conformational changes. However, they differ in the amount of proton translocation modules that the protein uses. The mechanisms also differ in the order of ubiquinoin protonation after it becomes reduced. Understanding the mechanism of complex 1 is important to possibly treat and cure mitochondrial diseases. Parkinson's disease has been connected to decreased complex 1 function due to reactive oxygen species. Other genetic diseases, such as Leber hereditary optic neuropathy and Leigh syndrome, exist due to different point mutations in various subunits.